The basic idea behind diversification is pretty simple. If you only invest in one company and that company takes a fall, your entire portfolio is at risk. If, however, your portfolio only consists of 25% of that company, you've minimized your exposure to the riskiness of that company. This is diversification. You don't want to keep all of your eggs in one basket. The more independent companies you invest in, the more diversified your portfolio is, and the less company-specific risk you are exposed to. A natural question to ask is, can we diversify away all of our risk? The answer is no. There is some risk that is present in every security in the market. It is called market risk. The way to measure the market risk, or non-diversifiable risk, of a security is to find its beta. It represents how volatile the security is relative to the overall market. Note, the beta of a portfolio is the weighted sum of the betas of the securities in that portfolio. The formula for beta is the beta of security A is equal to the covariance of A with the market divided by the variance of the market. This can also be written as the beta of A is equal to the correlation of A with the market times the ratio of the standard deviation of A to the standard deviation of the market. A beta of 1.0 means the security is just as risky as the overall market. Here's some general cases. If the covariance of A with the market is greater than the variance of the market, the beta of A is going to be greater than 1.0. That means it's more risky on average than the market is. If the covariance of A with the market is less than the variance of the market, the beta is going to be less than 1.0. So the riskiness of the security is going to be less than the average market security. The covariance of A with the market is equal to the variance of the market, then the beta of A is going to be 1.0. Those two are going to have the same riskiness in terms of this idiosyncratic company-specific risk. Investors that properly diversify their portfolios are still exposed to this non-diversifiable risk, so they expect to be compensated for it. The securities characteristic line tells us, for a given market rate of return, what risk premium an investor would require for the particular riskiness of his company. It is based on the beta of the security. So here we see a graph with the required rate of return for security A on the vertical axis and the required rate of return for the market on the horizontal. If the security has a beta of 1.0, we get this 45-degree ray through the origin. And that basically tells us for any rate along the x-axis, any market rate, if you go up to this line and over to the y-axis and find the return on A, you're going to get the same number. And this, again, is because a beta of 1 means that the riskiness of this asset, the security, is going to be exactly the same as the riskiness of the marketplace. Now, if the beta of the security is greater than 1, you're going to get a security characteristic line that looks like this. And this basically says if you pick a rate of return on the x-axis, the market, go up to this line and then go over to the y-axis, the return for security A is going to be higher because it's more risky. That's what a beta greater than 1 means. And if the beta is less than 1, it's going to be flatter. It's going to look like this. So for a given market rate of return, the required rate of return on security A is going to be less than that market rate. So how do we calculate this risk premium? Recall the equation for the nominal rate of interest of a security. R is the nominal rate, and it was equal to the risk-free rate plus some risk premium, which basically captured all of the risky effects that this security had that weren't present in the risk-free securities, basically things like treasury bonds. So if we know the risk premium of the market, we can multiply it by the beta of the security to find the risk premium of the security. That's basically what beta is. It's a multiple on the risk premium of the market that gives us the risk premium for the security. So the risk premium on the market is equal to the market's required rate of return, R sub m, minus the risk-free rate. Basically, it's the risk premium that's associated with the market over and above all of the risk that's associated with risk-free securities, things like treasury bonds again. So if we wanted to find the risk premium on security A, we would want to find the risk premium on the market, which again is the required rate of return on the market minus the risk-free rate, And then we would multiply it by this multiplier, this beta of A, that tells us in relation to the risk premium on the market how risky the security A is. The security's total required rate of return is the risk-free rate plus its risk premium. So it's the risk-free rate plus the risk premium on A, which by the above formula gives us the overall equation for the required rate of return on A. It's the risk-free rate plus the return on the market minus the risk-free rate times the beta of security A. This is called the capital asset pricing model, or CAPM, and it's used to predict an investor's required rate of return on a security. The graph of this equation is called the security market line, or the SML. So let's look at the security market line. On the y-axis, we have the required rate of return, and on the x-axis, we have the beta of the security. So here we see the security market line, and at a beta of 1, well, that's when we get the return on the market, because any security that has a beta of 1 gives us the same required rate of return the overall market has. This component is the risk-free rate. So basically, if you had a beta of 0, that would represent a risk-free security, again, like a treasury bond. And so we can see the vertical intercept of this line represents the risk-free rate because there's no additional risk premium built into the required rate of return. The beta is 0. And here is the market risk premium because, again, at a beta of exactly 1.0, everything in addition to the risk-free rate is inherent in the marketplace, and so it's called the market risk premium. Again, the nominal, the real rate on the market minus the risk-free rate, so this red area right here. As we increase beta, as beta gets higher than 1, we see that we have to be compensated for this additional risk. So any beta to the right of 1.0, if we go up to the security market line and over to the required rate of return, we're going to get a return that's greater than the marketplace. Over time, the security market line may change shape. Two factors affect this: expectations about inflation and the level of risk aversion. So first, let's look at inflation. If investors expect inflation to increase, the risk-free rate will increase because inflation is still a concern for people buying treasury securities. So the security market line will shift up, and that makes sense, right? Because the risk-free rate, again, is the vertical intercept of the security market line. So we'll get an upward shift in that security market line if we expect inflation to increase. If investors become more risk averse, they will require more return for a given amount of risk, for a given beta. So the SML will rotate up, which is an increase in the slope. So it'll look like this. For each beta, you'll have to require a higher rate of return to compensate for this new risk aversion. The equation for calculating beta doesn't change whether we're finding ex ante or ex post data. Only the variance and the covariance do, because if you remember back to the previous lecture, the equations for variance and covariance are different in ex ante and ex post. Suppose in ex ante the covariance of A with the market is 0.0115 and the variance of the market is 0.0085, where in ex post the covariance of A with the market is 0.031 and the variance of the market is 0.009. Recall the equation for beta. It's just the covariance of A with the market divided by the variance of the market. So in ex ante, it's 0.0115 divided by 0.0085. So in ex ante, the beta of security A is 1.353. In ex post, we use the ex post data, and it's 0.031 divided by 0.009. The beta in ex post of security A is 3.44. Instead of using the covariance and variance, we can calculate the beta of a security by running a regression on historical data, which is ex post data. The dependent variable of this regression will be the security's return, and the independent variable will be the market return. So it will be of the form: the return on A is equal to C, which is just some constant, plus the beta of security A times the return on the marketplace. The slope then will be the beta of the stock. As we see here, this equation that we're estimating using this regression is going to estimate the slope for us. And the slope, the coefficient on the return on the market, is our beta. So this is another way to find the beta of a security. Our calculator can actually do this for us. Let's look at an example. Suppose the following table shows us the return security A earned over the past 4 years, as well as what the market earned. So here we see years 1 through 4, the return that security A had in each year, and the average return of the overall marketplace in each of those years. To run the regression on the calculator, we have to enter in all the points. For each pair of points, we first enter in the independent variable, which is the market rate, then we press input, then we enter in the dependent variable, which is the actual individual security's return, and then we press sigma plus. We're just telling the calculator that we're entering in this pair of data, this coordinate, into a collection of data. So for us, first we would press 0.11 because that's the return on the marketplace in year 1. Then we press input. Then we press 0.15, which is the return security A earned in year 1. Then we press sigma plus to tell the calculator that we're done with this pair of data. Then we do the same thing for the rest. 0.09, the return on the market in year 2, input. 0.11 for A, sigma plus. 0.09 and 0.8, and 0.095 and 0.10. So those are, again, the first number just has to be the market return, and the second number has to be the individual security return. Now that the data is entered, we just need to calculate the slope. Press Shift Y hat M, and this will give you the intercept. Press Shift Swap, and you'll see the slope, which is the beta, and our calculator tells us is 2.79. We can use our calculated beta to find what return the stock should have earned, and then compare it to what it actually earned. Let's assume the risk-free rate was 3% over the past 4 years. Also, we can easily find that the average market return over the last 4 years was 9.625%. I just found this by averaging the 4 years of returns and dividing by 4. Recall the equation for the rate of return for security A. The rate of return given by cap M is the risk-free rate plus the return on the market minus the risk-free rate, that whole quantity is the risk premium of the market, times the beta for security A. So we found the risk-free rate, we're assuming it's 3%. The return on the market averaged 9.625%. The risk-free rate again is 3%. And the beta we just found to be 2.79%. So cap M tells us the required rate of return on security A is 21.48%. What was the average rate of return over the past 4 years for security A? So now we're asking what was the actual average rate of return? Well, if we average up the 4 pieces of data that we were given in the original table, we find that the average rate of return was 11%. So, since the required rate of return, which is based on the beta risk, was 21.48%, and the actual return was 11%, this security performed poorly. Jensen's alpha actually measures the excess returns of a security over its required return, so it compares what we expect to earn based on the beta risk and what we actually earned. It has the following formula. The Jensen's alpha is the average return minus your required return. In our case, the average return was 11%, and the required return was 21.48%. So the Jensen's alpha was negative 10.48%. And again, it's negative because our security underperformed. That's the end of part 4.